Hello students, welcome to the lesson 18 of the chapter 3 from the subject Advanced Structural Analysis. So in this lesson, we'll solve a problem from repeater interest range, sway type. Okay, so we are using the flexibility transformation approach here, and we have divided the problem into two parts. In this part, we'll do the entire problem. That's part 1. And in the next lesson, that's lesson number 19 in part 2, we'll just see how to develop the force transformation matrix and draw the shear force and bending moment diagram for the same problem. Okay. So let's get started. This is a problem given to us. See, this is a sway type. So why? Because there is a horizontal load here, and here the both the support conditions are different. So it will have a horizontal shift. So that's why it comes under sway type. Okay. So now let's start. There'll be no much variation if it is sway type or non-sway type. Okay. Step 1 is finding the degree of redundancy. Okay. So how many unknowns here? 3. And how many unknowns here? At least 2. The total unknowns are 5 minus how many equation of equilibrium will have 3. So this will be equal to 2, right? So let me write what are the unknowns here. We have VA, HA, MA and BD and HD. Right, what are the equations of equilibrium we have? Summation V equal to 0, summation H equal to 0 and sum of moment equal to 0. Because they are frames, all the 3 will come. Okay, that's your step 1. Then moving on to step 2, you have to choose the redundant. Okay, choose redundant. So what I will do is 2 is the degree of redundancy. So we have to choose 2 redundants. We'll choose these two at D. Okay, so we'll choose VD and HD as redundant. So once you choose the redundant, you have to draw the basic determinate structure. Basically remove those two reactions to get the basic determinate structure. Okay, so how will your basic determinate structure look? This is your basic determinate structure. So hinge has two reactions, so we have chosen those two reactions as the redundant. So I'm basically removing that. So this is how your basic determinate structure looks. So once your basic determinate structure is known, what you have to do is to assign the direction to your redundants. Okay, so assign directions to redundants. So how will it be? So a small diagram. So this is the basic determinate structure. Here we have to draw the redundants. So one is vertical, one is horizontal. So this will call as x1, this will call as x2. It is not compulsory, you have to take these directions only. You can take downward and leftward. You can take this as x1 and x2, just your wish. Okay, so this is what global coordinate. Right, once global coordinates are assigned, what is the next step you'll do? You'll assign your local coordinates. So assign directions to local coordinates. How will your local coordinates be? Every member will have two local coordinates. So there are totally how many members here? There are 3 members, so you have 6 local coordinates. So let us give the direction for each one. So this direction also is your wish. You can choose the way you want. Okay, so 1, 2, 3, 4, 5 and 6. So these are the 6 local coordinates we have. So once the local coordinates are assigned, we have to assign the W coordinates. So W coordinate depend upon what? The loading, external loading what we have. Okay. Assign directions to W coordinates. Right, how will it look? Now see here there is a horizontal, so compulsory we have to have a W coordinate there, and here we have a vertical load. So either here at B or at C you need a vertical coordinate. Along with that, compulsory we have to take the moments. Right, so your W coordinates will be, so first I'll take this as W1, then I'll take a moment here as W2, then one horizontal here as W3, and then one moment here as W4. So these are the four W coordinates. Here you don't have to take horizontal because it's already there here, and here you don't need vertical because there is no vertical force here. Okay, so this is how your W coordinate will be looking, right? So once that is done, what is the next step you will do? Calculate the extend moment along with the reactions. Why? Because if you see in global coordinate, there is horizontal and vertical coordinates. That's why we need to do it. Right. So let's start one by one. Now first for the span AB, what will happen for the span AB? No load. So your MAB will be equal to MB will be equal to 0. Then for span CD also, for span CD, MCD, MBC will be equal to 0 because there is no load. So only for MBC we need to do, right? So your MBC will be equal to MCB. That will be equal to what? WL by 8. That's your 100 into 6 by 8 point load at the center. Okay, 600 by 8, 75. So that will be 75 kilo Newton meter. Then your reaction, your RB will be equal to your RC will be equal to what? Total load by 2. So that's 100 by 2. That's 50 kilo Newton meter. So how will this look? I'm drawing only span BC. Okay, why? Because for AB and CD there's no values. So this load is getting the beam down. So in order to lift, take it to original position, we have to lift it up. So this is 75 kilonewton meter. This is also 75 kilonewton meter. Then we have two reactions. That's 50 kilonewton and 50 kilonewton. So this is your span B. So once this is done, what we have to do? We have to do our EQJL step 7 is what EQJL. So it's as simple as changing the direction of your extend moments. So this B, this is C, change the direction of the extend moments and put it, that will be your EQJL. So here it will be downward and downward. 95, 75, 50 and 50. Right, once this is done, what is the next step we'll be doing? Next step 8 is your load matrix. Right, first is your PE. PE will be equal to local into 1. So that's 6 into 1 in this case. Right, check all the local coordinates and compare it with your EQJL. You will get. So at 1 value will be 0, at 2 0, at 3 75, at 4 75. Directions are same, so positive. At 5 and 6 it will be 0. So 0 0 75 75 0 and 0. Understood? So that's your PE. Once your PE is done, you have to do your W matrix, which will be equal to W coordinate into 1. In this case, it is 4 into 1. Right, now check in those directions you need to see. So when you are doing PE, you have to just see EQJLs. Here we have to see EQJLs along with external load if any. Okay. Now, see, W1 is vertically down at C. This is A, B, C, and D. At C here there is no load, but here at C vertically down you have 50. That will be 50. Then W2 is what? Clockwise movement at C. Here it is anti-clockwise, so minus 75. Here there is no movement, so nothing will come. Then third one, W3 is what? A rightward force at B. Here there is no rightward force, but here you have an external load of 50, which is rightward, so positive. Coming to the last one, clockwise movement at B. This is also clockwise movement. Right, here there is no movement, external movement. So this will be your W coordinate. Understood? Now after W coordinate, what will you do? After your load matrix, what is the next step you will be doing? Find the element flexibility matrix. Right, now in the element flexibility matrix, there are three members. So for all the members we need to find. So first let us do for FAB. So what is the general formula? I'll write the general formula here for element flexibility matrix. It's L by 6EI 2, 1, 1 and 2. So for AB, what is the length? 3 meters by 6 E. I is I only into 2, 1, 1, 2. So that will be 1 by EI into 1, 0 0.5, 0 0.5 and 1. Next for BC. So for BC, what is the length? Length is 6. 6E. I is 2I in this case. Okay. Then 2, 1, 1, 2. So it will be 1 by EI into 1, 0 0.5, 0 0.5 and 1. And for the last one, F, what is that? CD. For FCD it is L is 3 by 6, EI is 2I, right? 2, 1, 1, 2. So that will be 1 by EI into 0 0.5, 0 0.25, 0 0.25 and 0 0.5. So this is FCD. Now once all these are all the element flexibility matrix are found, what we have to do next? What is your step 10? Step 10 is unassembled flexibility matrix. How will your unassembled flexibility matrix look? This will be of order 6 into 6. Why? Because there are three members, right? So how will you write? You should write FAB here, FBC here and FCD here. All other numbers will be 0. So that is how you will form your unassembled matrix, flexibility matrix. Okay, so 1 by EI, I'm taking it out common. So here it is 1, 0 0.5, 0 0.51, again 1, 0 0.5, 0 0.51, then 0 0.5, 0 0.25, 0 0.25 and 0 0.5. Right, so 0, 0, 0, 0. Then here 0, 0, 0, 0. Okay, 0, 0, 0, 0. So this is your unassembled flexibility matrix. So after this, what is the step 9? Now step 11. So step 11 is to form the force transformation matrix. So this will be of the order local into x plus w. Local, how many are there here? 6. X is how many here? 2. 2 redundants. W how many? 4. So it is a 6 into 6 matrix. Okay. Now I'm directly writing the values here. How do we get it? We'll see it in the next lesson. Also shear force and bending moment for the same problem I'll show you in the next lesson. Okay. So we have to take what? X1 as 1, X2 as 1 here. This is for Vx matrix. Then here W11, W21, W3 equal to 1 and W4 equal to 1. So this is called what? BW matrix. So I'm directly writing the values. Okay, 6, 6, 6, 0, 0, 0, 0, 3, 3, 3, 3, 0, minus 6, minus 6, minus 6, 0, 0, 0, minus 1, minus 1, minus 1, minus 1, 0 and 0, minus 3, 0, 0, 0, 0, 0, minus 1, minus 1, 0, 0, 0, 0. How we'll get this? I'll show you in the next lesson. Okay. Now, after that, what is that we have to do? What is the next step? Step 12 is to find the global flexibility matrix. So, what is the formula for global flexibility matrix? Capital F will be of the order what? Degree of redundancy into degree of redundancy. It's 2 into 2 in this case. Right. So, what is the formula? It's Bx transpose into unassembled flexibility matrix small f into Bx. So let me do the substitution. So Bx transpose is this transpose, right? So write it here. F is what? Bx transpose. That's 6, 6, 6, 0, 0, 0, 0, 3, 3, 3, 3, 0 into F. F is what? Ei. Already we have done here. So this is your F. 1, 0.5000, 0.5100, 0.50, 0.5100. The last is 0.5, 0.25, 0.25 and 0.5. This should be multiplied with what? Your Bx. 666,000,003,33330. Right, always you have to do these two multiplication first. So this is a 2 into 6 matrix. This is a 6 into 6 matrix. This and this are same. So you'll get a 2 into 6 matrix. 1 by Ei is common. Get a 2 into 6 matrix. What are the values? 9, 9, 6, 3, 0, 0. How will you multiply these rows with these columns? If you do, you'll get these results. Okay, 0, 3, 3, 3, 3, 0. This should be multiplied by this value again. 666,000, 0.33330. So this is a 2 into 6 matrix. This is a 6 into 2 matrix. 6 and 6 same. So we'll get a 2 into 2 matrix. So Ei into what will be the value if you multiply? How will you do this? You have to multiply these rows with these columns. Okay. So you'll get the result 144, 54, 54 and 40.5. So this is your F. That's your global flexibility matrix. So once your global flexibility matrix is done, what is that you'll do? Step 13, your F inverse. That's nothing but adjoint A by determinate A. So how will you do adjoint A by determinate A? You know already now how to do it. So it is 1 by this into this. That's 144 into 40.5 minus 54 square. This is what determinate F. Okay. Adjoint means what? Just change this rows into columns. This alternatively you change, and this you have to put it as a negative sign. I mean change the sign. So if you simplify this, you will get your F inverse. What is that? Ei. So your Ei will be on the top here. EI into 0.014, 0.0185 minus 0.0185, 0.05. So this is your F inverse what you will get. So once you are done with your F inverse, what is that you should find next? Step 14. So step 14 is to find your FW, which is Bx transpose into small f into Bw. Already we know Bx transpose into small f, we have found out here. So this is your what Bx transpose into f, right? So what are the values? Let me do the substitution. So it's 1 by EI into 996300, 1.53, 4.5, 4.5, 1.5, and 0.75. Here, okay, here done the calculation correctly, but I've written it wrong here. So let me just change. So this row, second row into these all columns we should do. So we will get 1.53, 4.5, 4.5, 1.5, and 0.75. Okay. Just while writing, I just did. Right, now this should be multiplied with what? Your BW. Where is your BW? Here. This is your BW. I'll show you in the next lesson how to get the BW. Okay. So for now, we'll write the values. Minus 1, minus 1, minus 1, minus 1, 0, 0, minus 3, 0, 0, 0, 0, 0, and the last one is minus 1, minus 1, 0, 0. So if you observe, this is a 2 into 6 matrix. This is a 6 into 4 matrix. So you will get a 2 into 4 matrix. So 1 by EI into what will happen? Minus 144, minus 27, minus 27, minus 18, minus 54, minus 13.5, minus 4.5, and minus 4.5. Okay. So this is your FW. Then what is your next step? Step number 15 is to find the redundant x, which is minus F inverse into FW into W. Okay, we can do these two first. So this is FW. Where is W? This thing only is FW. So where is W for you? This is W, right? So I'll just write it here only. So 50 minus 75, 50 and 75. So this into this you do, you'll get this. Already F inverse is there with us. EI, what is it? 0.1, 0.01 0.0185 with minus sign, minus 0.0185, and this is how much? 0.05. Okay, this is F inverse. FW into W is this rows into this column. So this is a 2 into 4 matrix. This is a 4 into 1 matrix. So this 4 and 4 is same. So you'll get a 2 into 1 matrix. So how much will you get? Minus 7875 minus 2250, right, into 1 by EI will be there. So this and this will get cancelled. So you have to multiply this along with this. So this is a 2 into 2 matrix. This is a 2 into 1 matrix. So you will get a 2 into 1 matrix. So your X inverse will be what? 67.758 and minus 34.58. So this is nothing but the redundance what we have chosen. Right, just check your redundance what you have chosen. X1 is vertical, X2 is horizontal. This is vertical up, this is right. Okay, so this is vertical up, positive, this is right, but we got negative sign, so this will be left. So this is your VD, this is your HD. So these are your redundant. So once you're done with your redundant, what is your next step you have to do? Find the final forces. So what is the formula for final force? Pf will be equal to what? Bx into x plus Bw into W minus your P E. So you have to do all the substitutions. You know all values. I'll just show you where all we have. Okay. So where is your Bx? Here. This is your Bx. Into x we have to do. Where is your x? Now we have calculated. This is your x. Right. Then Bw into W. So this is your Bw. W is where? This is your W. Okay. Then minus PE. PE is here. Okay, so if you substitute all this and simplify, simplification I guess you can do, it is easy. So you have to substitute all this and then simplify to get your final PF. Okay, then I'll just write the final values for you. So what all are we getting? Minus 47.70, 2.958, 2.958, minus 103.59, minus 103.59 and 0. So these are your final moments, end moments or final forces. Right now you write all this. What is this? This is MAB. This is what? BA. This is MBC. At same joint B, if you observe, they both are same values. Now because we are taking sagging hogging concept, these will be same here. But whereas you when you do in your normal stiffness approach, what will happen? One will be plus, one will be minus. Okay, you remember, right? So next, this is what MCB, this is what MCD, and this last one will be MDC. Now why is it 0? Because it is a hinge. You observe here, this is a hinge, so moment there will be 0. And here at joint C, if you observe, they both are same values. Then it is understood that whatever you have done is correct. Okay, so in the next lesson, what we'll do is, for the same problem, we'll see how to find the force transformation matrix B, how to calculate those values, we'll see. Then we'll draw the SFD and BMD. Okay, for the same problem, we'll do it in the next lesson. Thank you.